Section 6.6, Logarithmic and Exponential Equations. All right, we have encountered some very basic logarithmic equations and some very basic exponential equations in prior sections, but now we're going to ramp it up. Okay, we're going to look at more complicated logarithmic equations and more complicated exponential equations in this section. Okay, we're going to use the same techniques that we used for the basic equations, but now that we know those three major properties that we learned in the last section, 6.5, that's going to help us perform the work on the more complicated equations. Okay, so we will spend the first half of this section working on logarithmic equations, and then we'll spend the second half working on the exponential equations. Okay, we're just kind of expanding on what we've learned. All right, so let's jump into the logarithmic equations. So when you encounter a logarithmic equation, okay, they're pretty easy to spot. Okay, you're going to have a statement with an equal sign and it's going to have a logarithm in it. Okay, in this class, there are basically two types of logarithmic equations that you will encounter. Number one, okay, you're going to get an equation that can be written in this format. Okay, log base A of something is equal to a number. Okay, so basically you might encounter an equation where you can write it as 1 logarithm is equal to a number. Okay, your equation may not come in that format, but you're going to be able to write it in that format. Okay, the other type of logarithmic equation you may encounter in this class is the following. Okay, if you're able to write it this way, log base A of m is equal to log base A of n. Okay, so on either side of the equal sign, you've got a logarithm, one logarithm on either side of the equal sign, and they're of the same base. Okay, you have one logarithm equal to 1 logarithm. And the key here is that they have the same base. Okay, so those are the two types of logarithmic equations that you will encounter here. Okay, so again, the first type is you will get an equation that you can write, if it isn't already, in the form 1 logarithm is equal to a number. The other situation is where you're going to be able to take your equation and make it look like 1 logarithm is equal to 1 logarithm, and both of those logarithms on either side of the equal sign have the same base. Okay, depending on the situation, you're going to work them differently. Okay, so we're going to start with situation number 1. Okay, so that's what's outlined in the box. Okay, how to solve a logarithmic equation that can be written in the form log base A of m is equal to n. Okay, so again, this is situation number 1. Okay, let me write that over here. This is situation number 1, where you can write your equation in the format log base A of something is equal to a number. Okay, so 1 logarithm is equal to a number. Okay, these are the steps that you're going to follow to solve something like this. Okay, so let's go ahead and read through them. Okay, it says, number 1, if necessary, move all logarithms to one side of the equation and all other terms to the other side. Okay, so your equation may come with multiple logarithms. Okay, the key is being able to turn that equation into the workable format 1 logarithm is equal to a number. Okay, so to do that, you're going to start by moving everything with a logarithm maybe to the left side, and then everything else that's just a number to the right side. Okay, then in step 2, you're going to condense the logarithms into a single logarithmic expression using the properties of logarithms that you learned in section 6.5. Okay, so let's quickly reminisce about those 3 properties. Okay, remember the first property told you how to handle log base A of something times something. Okay, if you're taking the logarithm of a product, Multiplication turns into addition. So this would be log base A of m plus log base A of n. Okay. The second property told you how to handle log base A of a fraction. Okay. Division turns into subtraction. So this is going to break up into log base A of m, the top, minus log base A of n, the denominator. Okay. The third property, okay, told you how to handle the logarithm of a power. So if you have the log base A of something to a power, you are allowed to take that power and bring it in front of the logarithm. So this is going to be p times the log base A of m. Okay, those are those three major properties of logarithms we learned in section 6.5, and you're going to use them to condense your logarithms into one. Okay, that's why we spent time in section 6.5 talking about how to condense logarithms. This is why you need to know how to do that. Okay, so basically, like I said, in step 2, you're condensing all the logarithms into one. Okay, then in step 3, you're going to simplify the other side, so the right side of the equation. Okay, it should be just a single number. Okay, so once you've done steps 1 through 3, that should have resulted in an equation of the form log base A of m is equal to n, meaning you should have transformed your given equation into something that looks like one single logarithm is equal to a number. Okay, so once you've gotten there, you're going to use the definition of a logarithm in order to rewrite the resulting equation as an exponential equation. Okay, basically what you're going to do is you're going to do the arrow thing. Okay, once your equation looks like one logarithm is equal to a number, you're going to do the arrow thing on it. Okay, that's going to get rid of the logarithm, and then you're going to be able to solve for x in step 5. Okay, in step 6, this is extremely important for logarithmic equations, not for exponential equations. You need to check your solutions in the original equation. Okay, I've mentioned this before. You're not checking to see if your solution works out. What you're worried about is getting a solution so that if you plug it back in for x in the original equation, it causes you to take the logarithm of a negative number or of 0. And you can't take the logarithm of a negative number or of 0. So you're going to have to exclude any solution that leads you to taking the logarithm of a negative number or of 0. Okay, this is very, very important. Okay, with logarithmic equations, you may get something that looks like a solution, but it's actually not. So you've got to check. Okay, again, this does not apply to exponential equations. Okay, just logarithmic. Okay, all right, let's try this rule out. Okay, by the way, the other situation where you can write your equation as one logarithm equal to one logarithm with the same base, okay, we will get to that situation a little later. Okay, all right, so in example 1, it says solve each logarithmic equation. Express irrational solutions in exact form, which means no decimal answers, and also give it as a decimal rounded to 3 decimal places, okay, after the decimal point. Okay, so again, sometimes with these logarithmic equations, you can get some crazy looking answers. Okay, if you can give an exact answer, well, you should be able to give an exact answer, meaning no decimals, and then also give the decimal approximation. Okay, let's take a look at part A. Okay, the equation here is log of x plus 6 is equal to 1. Okay, as soon as you see this, this is an equation, you've got an equal sign, and you've got a logarithm involved. You see log. Okay, so this type of equation is exactly what I just described. Okay, on one side of the equation, we have a logarithm. On the other side, we have a number. Okay, so if that's the case, then we can go ahead. There's nothing to condense because there's only one logarithm to begin with. We can go ahead and apply the arrow method. Okay, so remember, this is log, so the base is understood to be 10, even though it's not written there. Okay, so this is really log base 10 of x plus 6 is equal to 1. So if we do the arrow thing, that tells us if we take the base and raise it to this power, meaning 10 to the first power, that has to equal this quantity right here, x plus 6. Okay, so that tells us that 10 has to equal x plus 6. Okay, the logarithm's gone. And this is really, really easy to solve for x. Okay, so this is a linear equation now. Okay, so we just need to isolate x. So I'm going to move the 6 over. Okay, so we're going to get that x is equal to 4. Okay, that's the solution. Okay, we're done. Okay, we do need to check ourselves. Okay, just to make sure that we don't end up taking the logarithm of a negative number or of 0. Okay, so I'm going to do a quick check over here. Okay, I'm going to plug in 4 for x in the original equation. Okay, and I'm not really checking the answer to make sure I get a true statement. I'm checking that if I do log of 4 plus 6, okay, I get the log of 10, and that's enough to check. I'm taking the logarithm of a positive number, so I'm going to be okay. Okay, you could go further and make sure that this is a true statement. The log of 10 is 1, which is the right side, so we do get a true statement. Okay, so 4 is the solution here. Okay, all right, let's move on to part B here. Okay, we've got a new logarithmic equation here. We've got log of x plus log of x minus 21 is equal to 2. Okay, again, we're trying to find the value or values of x that make this a true statement. Okay, so on the left side, you have 2 logarithms. On the right side, you have just a number. Okay, what we're going to do is we're going to be able to condense the logarithms on the left into 1. Okay, so then we'll have an equation that looks like 1 logarithm is equal to a number, and then we'll be able to do the arrow thing. Okay, so both logarithms on the left are base 10, so we can combine them. Okay, so remember the property. Which property are we going to use here? We have log plus log. Okay, so if you go back up to your properties, log plus log, okay, that's this property. Okay, we're using it backwards. If you're adding 2 logarithms of the same base, you can turn them into 1 logarithm through multiplication. Addition will turn into multiplication here. Okay, so on the left side, okay, we're going to retain the same base. It's still going to be base 10. We're going to get the log of, we're going to multiply these things together. Okay, so it's going to be x times the quantity x minus 21. Okay, you need parentheses here because x minus 21 is a package deal. Okay, this is how you condense the left side into 1 logarithm. Addition turns into multiplication. Okay, this is going to equal 2. Okay, so I'm going to simplify what's in brackets here. I'm taking the logarithm of, if I distribute here, it's going to be x squared minus 21x. Okay, so that has to equal 2. Okay, so now we've rewritten this equation as 1 logarithm equal to a number. Okay, as soon as you have that, you can do the arrow thing. Okay, so I know I've got log base 10 of x squared minus 21x is equal to 2. So if I do the arrow thing, this is going to tell you that 10 to the second power is equal to this quantity. Okay, so 10 squared is equal to x squared minus 21x. Okay, and the logarithms are gone. Okay, we now can solve this equation for x. Okay, so if we simplify here, we get 10 squared is 100, 10 times 10. That's equal to x squared minus 21x. Okay, if you quickly scan this equation, the highest power of x in the whole thing is 2, so this is quadratic. So we're either going to factor or use the quadratic formula, but we need to move everything to one side before we do that. So I'm going to move the 100 over. Okay, so I'm going to get x squared minus 21x minus 100 is equal to 0. Okay, I need to solve this for x. I'm actually going to factor here, but again, you could use the quadratic formula. Okay, this left side should factor into, let's see, x squared breaks down into x times x. And then I'm looking for 2 numbers that multiply to be negative 100, and they add up to negative 21. That's going to be negative 25 and positive 4. Okay, negative 25 times positive 4 is negative 100. And negative 25 plus 4 is negative 21. So this will factor into x minus 100 times x plus 4. Okay, and so you can actually multiply this out and do a check, okay, that this is going to work out. And when I check myself, it doesn't work out because I wrote the wrong numbers down. Okay, again, 25, negative 25 and the 4 are the numbers we're looking for, so it should be x minus 25 and x plus 4. Okay, so if you check yourself, you'll get x squared plus 4x minus 25x and then minus 100. Okay, so these two middle terms do combine to be negative 21x. Okay, all right, so that's how this factors into x minus 25 and x plus 4. Okay, so now we need to take each factor, set it to 0, and solve. So we're going to take x minus 25, set it to 0, take x plus 4, set it to 0, and solve. Okay, so we're going to get x can be positive 25, or if you subtract 4 from both sides, x can be negative 4. Okay, so you get two solutions here, but remember, we need to check them in the original equation. Okay, so let's come back over here. I'm going to do a check. I'm going to take each equation and just pop it in to make sure I'm not taking the logarithm of a negative number or of 0. Let's start with x equals 25. Okay, so I'm plugging into the original equation. Okay, so if I do log of 25 plus the log of 25 minus 21, okay, I'm going to be okay because I'm taking the logarithm of 25 and the logarithm of 4. Those are both positive numbers, so we're going to be okay. Okay, if I check the other solution, negative 4, let's see what happens. Plug it into the original equation. Right off the bat, we're going to have a problem. The log of negative 4, okay, plus the log of negative 4 minus 21, okay, we're taking the logarithm of negative numbers here. Okay, so we can't do this. Okay, what that means is that negative 4 looks like a solution, but it's really not. So we have to get rid of it. Okay, this is something called an extraneous solution. Okay, so we have to ignore this one. Okay, so the only solution here is x equals 25. Okay, and I'm going to write down this one is extraneous. It looks like a solution, but it's really not. Okay, so the only solution to this equation, and I'll put it right here, okay, x has to be 25. Okay, that's it. All right, let's try some other examples.